resolving forces, but we're using the force component approach. Previous class, we used the graphical method approach and the trigonometric approach. So this time around, we're using the force component approach. All right, let's go through. All right, so today we look at resultant of forces. And last one, in the previous class, we were looking at using the graphical method and the trigonometric approach. But this time around, we are going to consider the force component approach. All right. So this approach requires the forces to be resolved into rectangular or Cartesian components. So we are going to look at forces acting on the body, and we are looking at these forces acting on the body in space. Yeah. So each of the forces acting on the body in space, we must first resolve the forces into a rectangular component or a Cartesian component. The components are then summed to get light components are then summed to get the component of the resultant force. So this, for instance, you might have more than one forces acting on the body in space. You might have, let's say, force of Fx. So all the forces of x's might be like the px, qx, or xx. And might also have force of fy, might have py, qy, sy, and might have all the forces of, let's say, fz. You might have pz, qz, xz. So now, force p, which is acting on the body, force z, which is also acting on the body, force y, which is also acting on the body. We resolve all these forces, force k and force x. We resolve all these forces into their x component, their y component, and their z component. Because we realize that in spaces, in the 3D space, it is either we are on the x horizontal plane, the y vertical plane, or the z plane. So we resolve all these forces into their planes and the like component. So for instance, the x, ps, qs, xs will be added together for us to get the resultant force fx. And we come and add the xy together so that we get the resultant force fy. Pz, qz, xz, we get the resultant force fz. After that, we worked on the various forces to get the resultant force f. So this is what happens. In the force component approach. Now, magnitude and direction of the resultant force can be obtained through appropriate trigonometric techniques like we did on the other concept. All right. Now, resolving forces in the plane into rectangular components. So now I want to look at, first of all, the scalar approach. The scalar approach to resolve forces in the plane into the rectangular component. All right. Now, if you look at the diagram over here, we are looking at a force Fy and a force Fx. I want to find the resultant of this force. In the previous diagram, you could push this one over here, so we get something like this, Fx, Fy, and with the triangular law, you complete the third side as F to complete the resultant of this force. So now, say with this same diagram, let's draw the resultant force F over here. Now, this resultant force F, it's inclined. So we can look at the slope of the resultant force F. Now we take this as the slope. Let's consider the length from here to here as A, and the length from here to here as B, and the length from here to here as C. This is still on the resultant force F, and the angle it makes with the Fx as what? As theta. All right, when we do this, the force F here, because when we are looking at the ones we did in the previous class, force A of vector A, vector B, the resultant force here will be called A plus B. So now the force here, F, will become F is equal to what? F of X, the vector force F of X plus what? The vector force F of what? Of Y. Now, if you consider this diagram over here, this is F of Y, this is F of X, this is now the resultant force F, and here's the angle theta. and we want to find the trigonometric functions of these particular sides of this particular triangle, and considering the angle, we have something we usually refer to as the SOHCAHTOA. The SOHCAHTOA. Now, all right. So the sine is what? An opposite of what? Adjacent. This is something you should have in mind. The cos is what? Adjacent over hypotenuse. Sorry, sine is opposite over hypotenuse, and the tan is opposite over what? Adjacent. So right now, if you want to find the cos of this particular angle theta, so the cos of the theta will become your opposite, which is your Fy over what? Your the cos of is your adjacent, which is your Fx over hypotenuse, which is what? The resultant force F. The same way, the sine of your angle theta, which is your opposite, that's your Fy over what? Your F. And the tan of the theta, which is what? Your opposite, that is Fy over what? Your Fx, your adjacent. So now you can, from here, you can say Fx, that is the horizontal component of the resultant vector, is therefore equal to what? F cos what? Theta. So here you can also say Fy, the vertical component of your resultant force, is equal to what? F sine what? Theta. And here you can just keep it at the theta, which is the angle, can either be what? The tan inverse of what? Your horizontal component over your vertical component over your horizontal component. Now this is a similar thing we are seeing here over here. So now we are resolving this particular concept, finding the horizontal component of the force F, finding the vertical component of the force F, and want to find the angle, which is the angle theta. So here they use the cos inverse to find the angle theta. All right, so now we see this B over C because over here in the diagram, under the slope, we represent the slope sized by A, B, and what? And C. So if it is cos, then the cos of an angle, so representing it here, all right, representing it here, the cos of an angle over here, so we get something like this. This is the C, this is the A, this is the B. Yes, still the angle, because the angle is still the same here. Okay, Rouge is on the same straight line. So the cos of this particular angle is equal to what? B over what? Over C. That is opposite, so that is adjacent over what? Hypotenuse. B over what? Over C. B over C. So in putting this B over C over here, we get what? F times what? B over C. That is the cos theta is B over C. So we get F times what? B over C. The same happens to the sin theta, which is what? Opposite over what? Adjacent, A over C. So F sine A over C. So this is how we represent both forces in the plane into their respective what? Rectangular component. And this is what? A scalar approach. This is what? A scalar approach. A scalar approach simply means you are not using we don't mind the direction. So we are using the scalar approach. That is only the numbers on the sides, not necessarily what? The direction. So we get what? F of x is equal to what? F cos theta. And the cos theta, F of x is now equal to F into bracket B over C. B over C. All right. All right, now we are still resolving forces into their rectangular component. Still, we are looking at what? The scalar approach. Now, the same idea is extended to forces in space. So right now, we are not looking at only what? In the plane, okay, where we have the x and y axis. But this time around, I want to look at the 3D space where we have the x axis, the y axis, and what? The z axis. So this is the x axis, this is the y axis, and this is what? The z axis. Now, in these forces over here, it is a little tricky here. So I think you will have to get it so that you will all be on the same what? Page. All right. So let me just make it big, a little big. All right, so we are looking at resolving the same forces into rectangular component, the scalar approach. But this time around, we are applying the same idea to forces in what? In space. And the third component, that is Fz, is introduced. So this is what we actually want to look at. Let me make it big so that you get it. So we are looking at a force, the y plane, the x-axis, and the z. So when we have all the three at work, we are getting what? We are getting the spatial realm. So we want to look at a force acting within the y-axis, that is force Fy, and the force that is acting between the x and the z plane, we call that force Fh. So this force is acting between the x and z plane, we call that force Fh. All right. Now, the resultant of this particular force of the Fy and the Fh is called F. That is the vector force, what? F. That is the resultant of this particular force. So we say the angle between the Fy and the F, let's say is theta y. The angle between the x-axis and the Fh, let's call it phi. Let's call it phi. All right. We want to resolve this force over here into the vertical and horizontal component. So bringing this diagram down again, we have what? Our Fy. Let's call this our what? Fh. And we call this our resultant force F. And this is the angle theta what? Theta y. So in doing this, we say what is our theta y? So we have the cos of our theta y, which is equal to, we say the cos is what? Adjacent over what? Hypotenuse. So the cos of our theta y, what is adjacent will be what? Fy over what? The resultant force F. And the sine of our theta y, which is equal to what? Opposite, that will give what? Fh over what? Our hypotenuse, which is the resultant force what? F. So in finding the vertical component, which is the Fy, we get Fy then is equal to our resultant force F cos theta y, the angle theta y. And our Fh, which is the resultant component, horizontal component, will become what? Our F sine of what? Our theta y. So this is what we get over here. And this is the same thing they are getting over here. Fh is equal to what? F sine theta y. And the Fy is equal to F cos what? Theta y. Now, we are looking at resolving Fh, which is within the x and the z plane, into a rectangular what? Component. So we are resolving that Fh into what? A rectangular what? Component. And what do we get in resolving them it into what? A rectangular what? Component. All right. Now, this is what we get. F of x, which is the force acting over here, F of x and F of z, they have their resultant force as what? Fh. So now, if you look at here, and we are looking at the force F of x acting, and F of z also acting. The F of x and F of z will have their resultant force as F of h, which is the force acting within their what? Their plane. So now, to resolve F of h into the rectangular component, this is what we are getting. So that means we are resolving F of h into F of x and into F of z. So this is what we get over here. So we can pull it this way, F of z. This is what? Our F of what? X. And we get this as what? Our F of what? H. And we get the angle between the F of x and the F of h as what? Phi. So this is the angle between them. That is the phi. All right. So now resolving this is very simple. Cos of phi is equal to adjacent, which is F of x, over the resultant, which is what? F of h. Are we getting it? Are we seeing it? This is not the resultant. So the adjacent is F of x over this. And the sine of phi, which is equal to what? Opposite, which is F of z. Because if we bring it here, this will be what? Our opposite, the F of z. Over what? The hypotenuse, which is what? The F of what? H. So now what? What's F of x? F of x is therefore equal to what? F of h cos of what? Phi. And what is our F of z? F of z is then equal to F of h sine of what? Of phi. So now realize that in the 3D space realm, we've been able to resolve the vectors or the forces over there, okay, to all the components. So now we have f of y. So what was f of y? We got f of y as what? F cos theta what? Y. So we've been able to resolve the forces happening all in this spatial realm, f of x, f of z, and what? F of y. All right, so this one is that thing we get over here. That is the cos of phi. And so over here, we want to take the f of x, introducing what? Sine of theta y, and what? The cos of phi into that. So what do we get over here? F of x has been established to be what? F of h cos of what? Of phi. That is f of x. What do we get over here? What is f of h? F of h here is what? F sine theta y. F sine theta y. So that in place of f of h, we can put what? F sine theta y cos of what? Of phi. Please, are you getting it? So this will be the final thing we are having. And the same thing, f of z is also equal to fh sine theta, sine phi. So we can get what? Fh, which is what? F sine theta y sine phi. That will be our of what? Of z. All right, and that's what we are getting here, over here, this and that. Okay. All right. Now, we want to express, resolve the forces in the plane into their rectangular component. But this time around, we are looking at a unit vector approach. What we are doing earlier on, we are looking at what? The scalar approach. We are looking at what? The scalar approach. But this time around, we want to look at what? The unit vector approach. All right. The force is expressed as a product of what? Its magnitude and its unit vector. It's expressed as its magnitude and its what? Unit vector. So the concept here is knowing what? What is the unit vector? So we use this sign, which is the lambda, to represent what? The unit vector. The lambda to represent the unit vector. So which is very simple over here. I can just use this sheet to explain. So we have a force in the y direction. We have a force in the x direction. And the resultant force is what? F, which is over here. And this is the angle theta from the horizontal axis. So we say the force F is equal to, the vector force F is equal to force, the magnitude of the force times the unit vector. So we say vector force. So let me just do it this way. Vector force F, we put the sign there, is equal to the magnitude of the force, which is the magnitude of force, times the unit what? Vector. So the force is expressed as the product of its magnitude times what? The unit vector. And we are representing the unit vector with what? With lambda. With lambda. So therefore the force vector F is therefore equal to what? The magnitude of force times what? Times the lambda. And what is the unit vector? What is the unit vector? So anytime you have a force represented this way, the unit vector says that we represent the force in complex what? Numbers. So you have xi plus the yj, all divided by the square root of what? X squared plus what? Y squared. The square root of what? X squared plus what? Y squared. This is what? In unit vectors. I'm not doing mathematics here to prove why this is a unit vector. Okay, so you can go and look at it. So, you know, obviously, in what? In real number system, that's complex numbers. We deal with what? The real part of the complex number, and we deal with what? The imaginary part of the complex number. So the I and the J you see here are just imaginary numbers in some space in complex numbers. So the force F then becomes what? F of xi plus what? F of what? Yj. And we find the theta x, which will become what? Our force fx, the cos inverse of what? Fx over what? F. We've been doing this all over and over again. It's very simple. So the cos of that theta x is equal to what? The adjacent, which is what? Our f of x divided by the resultant, which is the hypotenuse. So therefore, the theta x will be equal to what? The cos inverse of what? The f of x over what? F. So that's what we've been doing. So put this in your head. If it's a three-space realm, you get xi plus yj plus what? Zk, all divided by square root of what? S squared plus y square plus z square. That'll be the unit vector. So put this in your head and we move on to the next one. All right. So like I said, for the Cartesian unit vector approach, that is the same thing that happened. So this is the 3D space. You have the x element or the x component, you have the y element, y component, you have the z element or the z component. So the magnitude of the force times xi, so this all is what? Equal to what? The lambda. This all is equal to the lambda, which is what? The unit vector. This one is equal to the lambda, which is the unit vector. So therefore it becomes f times xi. We get it. F times what? Xj. F times what? Zk. So this one is yj, sorry. So let's correct it. Yeah, if you have your slide, you can correct it. It's what? F times what? Yj. Fyj. All right. So now, over here, if you want to find the angle theta over here, this is the diagram. We want to find the angle theta over here. This is the diagram. Here is what? F of y. So it's more or less like we are having this particular diagram. Angle theta, cos of the theta is equal to adjacent, which is the adjacent, Fy divided by the hypotenuse F. So therefore the theta will be equal to the cos inverse of what? Fy over what? Over F. And that's why we are having over here. This is it. All right. Now, let's look at the resultant by summing component. The resultant by summing component. So like components are summed to obtain the components of what? Of the resultant. Like components are summed to obtain the component of the resultant. All right, so here's a typical example. Here's a typical example. What we have to do is that all forces that are acting on the body in space, we have to find the summation of all the forces in the x component or the x plane. We have to sum all the forces in the y plane, and we have to resolve all the forces in what? The z plane. So for instance, we have a force R, which is a resultant force we have to calculate. And we have forces like P, forces like Q, forces like S happening. Forces like P, forces like Q, forces like F happening. All right, so here, this is the scalar approach. So we take them, we sum all the forces in the x plane, we sum all the forces in the y plane, we sum all the forces in what? In the z plane. In the vector approach, we just have to introduce what? The unit vector. That's why we introduce what? The I, the j, and the k. It's obviously the same thing. And we look at the magnitude of the resultant force. So the magnitude of the resultant force is just the square root of what? All the resultant force, Rx, Ry, and what? Rz, the square of them. And the direction is very simple. If you are to have the diagram and I draw it, you realize that if you are finding the direction in what? The angle of x, theta x, it is Rx over R, the resultant R. If it's the direction in the angle of what? The y direction, it is what? Cos inverse of what? Ry over what? The resultant R. This is the resultant. And if it's z, it is Rz over what? The resultant what? R. All right. Still on the resultant by summing what? Component. So for instance, we want to look at this particular diagram here. We have forces acting on them in space. Okay, we have forces acting on them what? In space. And this particular one, we are looking at the force acting on them in just 2D space. In just 2D space. And we are looking at them acting in that the x axis space and the y axis what? Space. So if we are resolving this particular vector here, vector forces here, we resolve them only in what? The x component, and we resolve them into what? The y component. Resolve them into that, the y component. All right. So very simple here. This is what we'll be having. We have three forces, which is P, X, and Q. We have three forces, which is what? The P, X, and what? And the Q. And they are only in two planes right now, X and what? And Y. So these three forces, we say the R should be equal to what? Rx plus what? Ry, which is the same as the summation of all the forces in what? The X direction plus the summation of what? All the forces in what? In the Y direction. This time around, there's no Z plane over here. So we don't solve for any forces in what? In the Z. And we said if it is R, then using the summing component, we sum all the like forces Px, Qx plus Xx I plus what? The Py plus Ky plus what? Syj into it. Now, our problem here is for us to look at the forces in the Px. So if you look at this is a force P that is acting on the body. And this force P has been resolved into what? Px I, and it was resolved in what? Pyj. So if you can see, so the force P here was resolved into the horizontal component and the vertical component. This was force X. It was resolved into what? The vertical component, which is xi, and resolved into the horizontal component xxi, and the vertical component, which is xyj. And this is the force Q, which was also resolved into what? Here as what? The horizontal component qxi, and it was resolved into the vertical component as what? Qyj. But always take note, coming down, if here is the center, then if it's coming down, it should be negative. If it's going here, it should be positive. If it's going here, it should be negative. And if it's going here, it should be what? Positive. So this is a positive plane. This all out negative what? Planes. It's something you should also keep in mind. So if that happens and we get all the forces, so for P, we have Px, Qx, we have Px and Py. For X, we have Xx and Xy. For Q, we have Qx and what? Ky. So if you want to look at the direction very well, for P, the Pxi will be what? Positive. Pyj will be what? Positive. For X is happening, so Xyj will be what? Will be positive, but Xij will be what? Negative, because it's going in the negative what? Plane of the x-axis. And for Q, the Qyj will be what? Will be negative, but the Qxi will be what? Will be positive. So it's something you should know. And if you have to find the resultant force, which is this, it is the root of what? The Rx square plus what? Rxi square, Ryj what? Square. And if you want to find the angle, each of them, if it's theta x you want to find, it is the cos inverse of what? The Rx over what? R. If you want to find the theta y, it is the cos inverse of what? Your Ry over what? Over R. All right.